Hi everyone, Araz here. I'm a PhD student in University of Tübingen and I'm working with Dana Wolfle. And today I'm going to present you our recent publication, which is about the in vitro muscle fiber experiments in realistic boundary conditions, and we are looking for the muscle reflex response. So, I'm always amazed how we are capable of performing effortless leg locomotion on rough terrains with our really complex neuromuscular structures, which is our bodies. And even though this system has a neural delays as a built-in thing, we are able to deal with unexpected perturbations on the road, like step downs, or maybe some stones on the road, or sometimes your kid might be the perturbation on the road. But how we manage this? So previous simulation and in vivo experiments studies show that contribution of zero delay intrinsic muscle mechanical properties are playing an essential role in motion stability, but none of these studies can explain how muscle fibers exploit intrinsic mechanical properties while responding to perturbations during realistic stretching conditions. So this is our research question in this paper. Sorry. And to answer this question, we built this nice methodology. So we perform human hopping simulation with a single leg hopper, which has a single heel type muscle model on top of it as a Araz muscle, and we stimulate this muscle with an orange dashed line you see at the top, at the mid here, with a stimulation profile given here, which has a 30 milliseconds delay in it. And we perform this simulation for 3 different perturbation levels, and we extract the lengthening of contractile element and the contraction velocities throughout the hopping cycle. And then we use this kinematic data and the constant activity level at the preflex phase for our in vitro muscle fiber experiments and our isolated contractile element simulations. But today I want to focus on the in vitro muscle fiber experiment results. So here you can see the work loops that we obtained from the muscle fiber experiments for 15% activity level. The thick lines are representing the preflex phase, and the thin lines are showing the continuation of the preflex, continuation of the stretch shortening cycle. And from light blue to dark blue, you can it goes through step up to step down perturbation. And I want to split the work loop into pieces. So when we look at the initial 2% length change, we realize that at this phase we have the peak velocities due to the impact. However, the force response is not changing at all. So this shows that the initial response of the muscles are elastic, and it comes from their short-range stiffness property. And we realize that at this range, at the velocity range that we are working, actually the short-range stiffness is independent of velocity. So the velocity has no impact on the short-range stiffness in the velocity range that we are working. And then you can realize that there is a deviation starts after the short-range stiffness phase, and we want to understand what's going on at that phase. So we kept the area which is the end of short-range stiffness and the end of step-up perturbation, because at this phase the elongation amount for each perturbation is same. So whatever difference we see, it's coming from the velocity effect, which means it's the damping effect. So at this phase, we realize that there's a velocity adaptation in force response. However, when we look at the work done by the muscle fiber, there's a slightly difference, but it's not significant. So then the question comes as, is there a significant difference between the perturbation responses? And yes. So when we look at the preflex work, like whole preflex work, we realize that there's a significant difference between step up and step down perturbation. But this not comes from the short-range stiffness, it's not coming from the damping. And when we look at the overall response, we realize that actually the main contributor to the preflex work is the amount of stretch due to the perturbation. So how much you stretch the muscle is the main important thing which creates the significant difference between the perturbation levels. And the other question we had, you can see that there are different activity levels over there, so why we conduct these experiments. So previous studies show that if we arrange our activity level to the touchdown case due to the, according to the perturbation, actually we can reject perturbation in a better way. So if we can tune our muscles, we can obtain a better perturbation rejection. And we want to test this. And we realize that with the activity change, we can we see the preflex work is increasing. And also when we look at the mechanical features of the muscle, we can tune our stiffness and we can tune our damping by changing the activity level. So these are the main results that we found for our muscle fiber experiments, but in the paper we have a lot of results more. So thank you for your attention. And if you have more details, here's your address. You can go to the paper and you can check our results, and there are like really interesting results came up. And if you have any questions, as Matthew says, clear your mind of questions. Yeah.
Thank you. Do you have any idea how to apply this kind of fighting to robotics walking?
Actually, this is a continuation work that we are working on. So we want to implement this force response analogy with a spring damper system on a one-leg robot, and to see how morphological computation is actually reducing the control effort of our robot. So this is a protocol. So we have a collaboration with Max Planck Intelligence Systems, and the team over there is right now working on this. Currently, they published several papers on the damper system, but still this project continues. So I hope soon we can share this with you.
Time for one more question.
You said there was a phase where the damping component was contributing the most. Is that correct?
No, it's the phase of after short range stiffness. There's a force deviation. The force deviates due to perturbation, and there's a slight difference in the work, but it's not significant. There's no significant difference between perturbation levels. But if you tune your muscle, so between the activity levels, like different activity levels, you can tune your damping system. But the difference due to the perturbation, of course, this might be due to the perturbation that we are working. So we work in 5 centimeter step up and step down perturbation. So if you enlarge this, the significant difference will be higher. But in the range we are working, there's no significant difference in the damping response.